In this video, we're going to continue looking at recursive definitions. In particular, we're going to start looking at recursively defined strings. Before we do that, let's review what a string is. Now, again, in a previous section, I think it was section 2.4. Yeah, I think it was 2.4. We had defined this and didn't really do much with it. We said a string is a finite sequence of characters from a finite set, and they call that finite set an alphabet. And the example we had used was, let's say that we have the string A, B, C, D, E. So that is a string of length 5. String. Wow, I like put two words together there. String and length made strength. A string of length 5. There we go. Length 5. Okay. Now, I also had mentioned in the notes, but I want to write this down, that we do have what's called like an empty string, like an empty set, but the empty string, and we use lambda to represent that. So lambda is the empty string. So that's the Greek letter lambda. All right. Second note I want to mention, note number 2, and I did not mention this in the previous section. There is a special kind of string called a bit string. And a bit string is a string that consists of zeros and ones. Is a string of, not S, of 0 and 1. So for example, a bit string could be like 0, 1, 1, 0, 0, 1, 1, 1. I don't know, however you want to make that look. But there you go. That's a bit string. Okay, now that we've got all of that under our belt, we haven't really done much with strings, and now we're going to do a little bit more. They are going to define this sigma star. So this is the Greek letter sigma, sigma star. So sigma star of strings over the alphabet sigma. Okay, so here's the basis step. Lambda, the empty string, is in sigma star. And the recursive step is if W is in sigma star and X is in sigma, then WX is in sigma star. Now, this doesn't mean multiplying, because what we're doing is we're putting together the characters of the strings. That's what that represents. So, for example, if sigma is 0, 1, then the strings in sigma star are bit strings. Okay, so we start with lambda, and because this statement, the recursive statement, says that what we have in sigma star, in this case lambda, and then we have something in the sigma, which let's say is 0. If we put the empty string and 0 together, what do we get? 0. If we put the 1 together with lambda, then we get 1 in sigma star. If we put, now since 0 and 1 are in sigma star, both of these are now in sigma star, then I could pair 0 with 0 and get 0, 0 in sigma star. And I could pair 0 with 1 and get 0, 1 and 1, 0 and so forth. So we can start making combinations every time we build up something new to be in sigma star. Let me kind of show how that works with this example. So let's say sigma is AB. Let's show that AAB is in sigma star. So first thing we're going to start with is the only piece of information we know, and that is lambda is in sigma star. So we start with this. Lambda is in sigma star. Okay, so we know that, and we know that A is in sigma. Those are the two pieces of information we are given. They told us sigma, so A is in sigma, lambda is in sigma star. Now I'm going to use that from the recursive step, and I'm going to put lambda together with A. So since lambda doesn't have anything in it, that means that the characters of A is just A, and A, oops, let me say then A is in sigma star. Okay, so now that I know that A is in sigma star and A is in sigma, I can pair those two together, which is going to be the characters AA, And now those are in sigma star. Cool. So now that I know that AA is in sigma star and B happens to be in sigma, I compare those characters together. Then AAB is all in sigma star. And I can keep producing new strings by just pairing together the previous strings in sigma star with A and B. So I get strings of A's and B's that however I want to form them. I can get them in sigma star. And there you go. Okay, so the concatenation of two strings. So two strings can be combined via the operation of concatenation. Let sigma be a set of symbols and sigma star be the set of strings formed from the symbols in sigma. We can define the concatenation of two strings, which we use the times symbol to do, recursively as follows. So if something is in sigma star, then we can do that, that W, which is a string, by the way, the string times, or the concatenation of the string with lambda ends up giving us the string back, W. So here's the recursive step. If we have another string in sigma star, W1, and a second string, W2 in sigma star, and X happens to be in sigma. X, by the way, these are just characters. So this, when it says X, it really is referring to a single X, okay? X is just a number. It's a character. Because that's what they said sigma is. Sigma is the symbols. Then we can take and do X at the end of the string for W2 and do a concatenation with that and W and the string W1. Or I could do the concatenation between W1 and W2, whatever that comes out to be, and that then tag X on at the end of that string. And by the way, these concatenations, when we write the dot, we often don't, just like with multiplying, we often just drop that and just write the two strings together. So for example, here, if W1 is abra and W2 is cadabra, the concatenation is abracadabra, putting the two strings together, literally one right after the other. We're taking those characters and putting them in a line. Okay. Now we're going to talk about another recursive definition that we're going to create based on the length of a string. So we know what we talked about earlier is we count up how many characters are in the string itself, right? Okay, so the basis step is going to be finding the length of lambda, which is 0 because it's empty. The recursive step looks like this. So if I want to find the length of here, sorry, I'm going to backwards write this. They kind of do it different. If I have a string in sigma star and I'm going to take a character out of sigma. Okay, so I have a string in sigma star, I'm going to take a character out of sigma. Then if I want to find the length of the string from sigma star and tag on the character X at the end, that is going to be the length of the string sigma, I'm sorry, the string of W, whatever that string is, plus 1, because I added a single character, in this case, X. That's how we define the length. Okay, now we're going to define well-formed formulae. So formulae is the plural of formula. So the set of well-formed formulae in propositional logic involving true and false, propositional variables, and the operators. So this is all the stuff we looked at the start of the course in 231. We can write a well-defined formulae for these. So the basis is to say that if we have true, false, and S, where S is some propositional value, that we're going to say that these are well-formed formulae. The recursive step is to say, okay, so if E and F happen to be well-formed formulae, then we can add those operators on, and those operators are going to give us well well-formed formulae as well. So as they state down here, to say that P or Q implies Q and false, that's a well-formed formulae, but putting PQ and just pairing it with a single and not putting anything after that, that is not well-formed. There has to be something at the end. So that would not qualify as a well-formed formula. It's not just throwing these operators in, it's using the operators correctly. We put the negation in front, we put the and or the or in between, we use the implication symbol, and we use the equivalence symbol. It has to be an equivalence between two well-formed formulae. All right, so there we go. That's a definition that they kind of introduced there. All right, now the next definition are rooted trees. Now we're going to talk more about trees in chapter 11, but they're going to kind of introduce the terminology to us now in the form of recursive definitions. So rooted tree is a set of vertices, distinguished as a vertex called a root, and edges connecting these vertices. So the basis is to start with a single vertex, which is a rooted tree, and then we can have these disjoint rooted trees that we can put together using edges, and those form new rooted trees. Here's a visual of that. We start with this kind of single vertex R, and we can connect it to other trees using edges, which we represent with a line here. So we can connect it to one tree, two trees, three trees, four trees, as many trees as we want till we get to n trees. And then we can repeat those connections as many times as we want as well. So we can then connect any of those trees to other trees and use these edges to keep connecting these vertices together. So we form these patterns of rooted trees. Now, the way that we allow these rules of connection does change. So the first type of connection or change in these connections are we're going to look at what's called extended binary trees. All right, so a set of extended binary trees can be defined recursively, saying that we have the empty set is an extended binary tree. If T1 and T2 are disjoint extended binary trees, there is another extended binary tree that we can create between them, T1 times T2. That's what that says. We're taking those two together. And we can connect, it's the root R together with the edges connecting the roots with the left subtree being T1 and the right subtree being T2. And we can have trees that are non-empty. So here's interesting to note about extended binary trees, because here let me just scroll down and show full binary trees. Full binary trees is almost the same definition, except the basis step is that we start with a single vertex R, whereas in the extended binary trees, we can start with the empty set. So in extended binary trees, we can have these kind of empty subtrees. So in extended binary trees, we can have empty left or right subtrees. So let's look at how that visually looks different. So here's the extended binary trees. So these are the extended binary trees. So we start with the empty set, then we can form a tree, and then we can choose to connect that tree to two other trees or not. We can choose to connect it to one tree or the other tree. That's what those little symbols are showing. Then we can choose to connect two of them down the left subline and just the one on the right, nothing else. Or we could do one on the left subline, then the right subtree line, and then we do a right subtree line, and we kind of get this pattern. So what we have are these kind of interesting creations where we can stop and not do both at the same time, or we could do both at the same time where we branch them both out, or we don't. All right, we can do weird connections and patterns with it. With the other one, when you start connecting a left and right, you will always have a left and right. Now, it could possibly end. In other words, maybe there is no other subtrees to connect on this left subtree here that I'm looking at. This one doesn't have anything to connect with, but the right one did, so we connected it. All right. And it always goes in twos, whereas this one could be singles. We can have these single lines kind of extending down, and there's nothing wrong with that. So that's the difference between full and extended. All right, we'll talk more about trees later. We're going to get into structural induction. So this is like our last major thing that we're going to look at with induction. Before we do that, we're going to use mathematical induction one more time from section 5.1 to do this example. So let's show the set S that we defined earlier, where 3 is an S, and if X is an S and Y is an S, then X plus Y is an S. We're going to show that this set is going to only give us multiples of 3. All right, and it has to do with the fact that the basis step gives us a 3 to start with. Now, in order to show that S is only multiples of 3, in order to do that, I'm going to create the set that are the multiples of 3. I'm going to call it A. So A is in the form 3n, where n is a positive integer. So here I'm going to write that. N is a positive integer. And what I'm going to do is I'm going to show that S and A are equal. So the way I'm going to do that is use the subsets. First thing I'm going to do is show that A is a subset of S, and then I'm going to show S is a subset of A. So to show that A is a subset of S, I'm going to use induction. Okay, so here's how I'm going to do it. Step 1, P of 1. Oh, let me start by saying what P is. if I'm gonna do this, sorry, before I do that, P of n is the proposition. That 3n is an element of S. Oops, that everything that's a multiple of 3 is going to end up being an S. Positive multiple of 3. It's going to end up being an S. Okay, so first thing I'm going to do is show that P of 1 is true. So P of 1 is the multiple 3 times 1. And 3 times 1 is 3, which I happen to know is an S because that's my basis step. Done. P of 1 is true. Okay, so now I'm going to show, or I'm going to assume that P of k is true. Assuming that's true, which means I'm assuming that 3k is an element of S. So 3k is an element of S. I want to show that k plus 1, that P of k plus 1 is true. All right. So I'm going to kind of shortcut how I'm writing this. So by the recursive definition that we formed, or were given by the recursive definition, oops, that doesn't look like a D. Let me clean that up. Definition. By the recursive definition, we know that 3 is an S, and we have assumed that 3k is an S. So therefore, the recursive definition says that 3 plus 3k is an S. If I add them together, that's an S. Okay, let me write that a little differently. A better way to write that is 3 times k plus 1 is an S. So I factored out 3 and I reversed the k in the 1. But look, what's that? That's P of k plus 1. So P of k plus 1, oops, is true. And we did it. Oops. So we were able to show that P of k plus 1 came true based on our assumption. All right, so step 2 is kind of funny because it's kind of obvious. So I'm going to show that S is a subset of A. I'm going to show that if it's in S, it's also going to be in A. So what we're going to do is we're going to use the recursive definition of S. So using the recursive definition, of S of S. So by the basis step, we know that 3 is an element of S. They gave us that, but we also know that 3 is an element of A. Right? So 3 is an element of S and 3 is an element of A. So what that does then is that means that we've set this thing up so that because 3 happens to be in both S and A, and it's the only element they gave us in S, we're building on that element from here on out. So further, all the elements then, all elements in S are divisible by 3. And therefore in A. In particular, the very first element that they gave me, 3. Now on the recursive step then, so the recursive step, so we're going to tackle what happens with each of these elements. We know that X plus Y, which is formed by taking what we know is an S, which happens to only be 3, this is also divisible by 3. Why? Well, because if X and Y happen to be in S to start with, which is just 3, because we have to start with 3, then we know 3 divides both of them, because everything that happens to be in S right now is divisible by 3. 3 goes into both of them. And therefore, 3 goes into their sum. We showed this in chapter 4. We proved this, that if you sum them up, they work. So we're done, because now we've basically shown in the recursive step that everything is going to be a subset of, everything is going to be a multiple of 3 or divisible by 3. So S is a subset of A, and we're done. S is now equal to A based on that. So let's talk about structural induction then. So to prove a property of elements is recursively defined using structural induction, we show the result holds for all the elements specified in the basis step. Then we show that if the statement is true for each of the elements to construct the new elements in the recursive step, the result will hold for the new elements. So that's kind of what we did here. We showed that when we built up in the recursive step, that we were able to have it maintain then for the new elements. So let's look at an example for structural induction. Before we do that, they want to introduce a couple of new terminologies for binary trees. So the height of a binary tree is defined to be if T is only a root, then its height is 0. That's what that says. If T1 and T2 are full binary trees, then the full binary tree T1 times T2 is the height of 1 plus the maximum height of those two. So putting the two of them together forms a new height on our tree. And we say whatever the maximum height for T1 and T2 is, that also contributes to the height of the tree. So if T1 and T2 had happened to be already somewhat formed, right? Boop. So there's, let's say that's T1, and I combine that with T2. Boop. So they kind of end up combining in together. We take the maximum height here, which was already 2, and then we add 1 to it. So for the new combination of the two together, I hope that makes sense. All right, we're just going to use their definitions though to do the structural induction. It's kind of nice. Again, we'll talk more about the trees and the binary trees and all that fun. Oops, later. Sorry, hit backwards too many times. Okay, now the number of vertices, that's how many vertices that you count up on one of these trees, okay? If I wanted to write this as a recursive formula, here's how it's going to look. The basis is going to be the number of vertices, of a full binary tree T consists of only one root, or consisting of only one root, will have only one vertice to count. So n of t is 1. Now here's the recursive step. Sorry, recursive step. Okay, here we go. If T1 and T2 are two other full binary trees, then if we put them together, which is also a full binary tree, has the number of vertices of adding, oops, not a 1, but a t, of adding the two trees together, their vertices, plus an additional 1, because we brought them together to form T. All right, there we go. So that are two things we're going to use to do a structural induction example. So here is the theorem. If T is a full binary tree, then the number of vertices is going to be less than or equal to 2 raised to the height of the tree plus 1 in its exponent, and then minus 1. Okay, here's what's kind of cool. I don't really need to understand what it all is visually. We'll hash that out in chapter 11. I'm going to use these definitions to just show that the structural induction works. So I'm going to proof by structural induction. All right, here we go. First thing, basis step. I got to show that the basis step works. So the result holds, oops, the result holds for a full binary tree consisting of one root. Consisting of one root. Because, so this is, if we're working at one root on a full binary tree, from this, we happen to know n of t is going to be 1 and h of t is going to be 0. They told us that up above. So it's going to hold that if I look at n of t, which is 1, that is going to be less than or equal to 2 raised to the h of t plus 1 minus 1, which is 2 to the 0 plus 1, which is 2 minus 1, which is 1. It works because it's less than or equal to 1. So 1 is less than or equal to 1. Done. Basis step holds. 2. So here's the recursive step. I'm going to assume it's going to hold for the new elements that we form. In this case, I'm going to assume that T1 and T2 it works for. So T1 is less than or equal to 2 to the h T1 plus 1 minus 1, and T2 is less than or equal to 2 times the h of t2 plus 1 minus 1. Boom. Okay. And these are T1 and T2 are full binary trees. Or full, I'll say it, binary trees. T1 and T2. Okay, cool. All right, now here we go. What I want to show is that n of t is going to end up equaling 1 plus n of t1. Oops, that looks like an h. Sorry. Let me fix that. It's n of t1 plus n of t2. So I want to show that n of t is less than or equal to this 2 to the h of t plus 1, right? I'm going to try to show that this is going to happen. So I'm going to start with what I know n of t is from the definition. Okay, so this is, let me write that down. This is from the recursive definition. The recursive, they called it formula, recursive formula of n of t. So that's where I got that from. That's from right up here. Cool. All right, now I can say then that this is less than or equal to 1 plus 2 to the h t1 plus 1 minus 1 plus 2 to the h t2 plus 1 minus 1. And that's by assumption. I assumed that. All right, now here's where we are going to get creative. So whichever one happens to be bigger, whichever number comes out bigger, the one for T1 or the one for T2, whichever one comes out bigger, I'll call that number the maximum of those two. That means I could rewrite this instead of saying 2 different 2 to the h plus blah, blah, blah. I can write this as 2 times the maximum of those two numbers. T1 plus 1 or T2 plus 1, whichever one comes out bigger. Now, these both have minus 1s. I don't want to forget, both of those have minus 1s. So minus 2. So that's me putting these two together and calling it whatever the maximum one is. Let's pretend it works for both. Okay. So what I have basically said is that the sum of two terms is at most 2 times the larger. That's what that's assuming there. So if this one happens to be the bigger number, great. I'm going to say 2 times that. So if it happens to come out to 5, then I'm going to say it's 2 times 5. And this happens to be 4, great. I'm going to use 2 times 5 to represent the inequality, whichever one happens to be bigger. All right, get rid of that underline. Okay, here we go. Now, this is using an idea that rather than talk about the max of these two numbers where it's 2 raised to these 2 different exponents, it makes more sense to clean that up and say instead, okay, here, I'm going to take this 1, by the way, really quick. I'm going to take this 1 and I'm going to combine it with this minus 2. So those two are going to come out to -1. All right, which I'm going to write it as a combined. Okay, so plus, now instead, I'm going to write 2 times. And so I'm going to put 2 to the maximum of those two numbers instead. So really, I'm forcing it to look at which one's bigger, h of t1 or h of t2. Plus 1, and there we go. So I'm kind of rewriting it. So this is the 2 here. And this 2 came from the fact that these were both 2 raised to those powers. So I'm using, here's what I've done. I've said that the max of 2 to the x and 2 to the y can be thought of as 2 to the max of x and y. That's what I've done there. All right. Okay, we're almost done. Here we go. So the max of these two plus 1, this statement right here, let me actually highlight it. This statement right here was the statement we made earlier about the height. Boom. So this is what we call the height of T, where T was a combo of these two, T1 and T2. So this is then, here, I'm going to write the -1 afterwards. So 2 times 2 to the height of T, and then I'm going to put the -1 at the end. Okay, but here, 2, oh, actually, I don't need the less than or equal to sign. Oh, please don't get mad at me. Oh, you're so good. Okay, good. It gets so upset sometimes when I use that feature. Okay, so when you have 2 to the 1 plus HT, I can just write that as 2 to the HT plus 1 minus 1. I'm bringing those together. Okay, we did it. Look, look, look here. We said that N of T is less than or equal to, boom, yay. So we finished. We have done the proof. Good job.